Have you ever found yourself stuck trying to find the shortest path in a complex graph? It can be quite a challenge, right? If that's you, then you're in the right place. Today, we're diving into a modification of Dijkstra's algorithm to help you compute shortest paths efficiently. I totally understand how frustrating it can be when you're working with weighted graphs and need to optimize your pathfinding. You're not alone in this. Many developers face similar challenges when dealing with graph algorithms. Here's the specific question we're addressing today. One user asked, how can I modify Dijkstra's algorithm to compute the shortest paths from a given source vertex in O of v times w plus e time? This is a great question, and one that many people encounter when optimizing their algorithms. So what does this mean? Essentially, we need to adapt Dijkstra's algorithm to handle graphs with non-negative weights that can vary. This modification allows us to efficiently compute shortest paths even when weights are not uniform. And stick around. At the end of this video, I'll share a crucial tip that will help you implement this modification seamlessly. To modify Dijkstra's algorithm for our specific case, the user should first understand that we need to handle weights that can range from 0 to a maximum value w. This means we will use a different data structure to manage our priority queue. Next, the user should implement a bucket-based priority queue. This will allow us to efficiently manage the vertices based on their distance values. Each bucket will correspond to a distance value. Now the user should initialize the buckets and add the source vertex to the appropriate bucket. This is crucial for starting the algorithm correctly. After setting up the buckets, the user should implement the main loop of the modified algorithm. This loop will process each bucket in order, updating distances and moving vertices to the appropriate buckets. Finally, the user should ensure that the algorithm correctly outputs the shortest paths from the source vertex to all other vertices in the graph. This will complete the modification of Dijkstra's algorithm. Fun fact: Dijkstra's algorithm was conceived by Edgar W. Dijkstra in 1956, and it's still one of the most widely used algorithms for pathfinding today. Talk about timeless. Now, let's look at the answers provided by other users. An alternative approach to modifying Dijkstra's algorithm is the dial algorithm. This method is efficient for graphs with small weights. Instead of using a priority queue, it utilizes buckets for each weight from 0 to the maximum weight. The complexity of this algorithm is O(m plus n times c, where n is the number of vertices, m is the number of edges, and c is the maximum cost. Another suggested method is the radix heap. This approach organizes edges into buckets based on their weight ranges. The complexity for this algorithm is O(m plus n times log of n times c. The user also conducted performance tests on these algorithms, providing insights into their efficiency. 4 tests were performed to compare the results. Here's the tip I promised. Always ensure your priority queue is implemented efficiently. This can drastically reduce the time complexity of your modified algorithm. And there you have it. You now know how to modify Dijkstra's algorithm to compute shortest paths in O of v times w plus e time. Remember, practice makes perfect. If you found this video helpful, hit that subscribe button for more algorithm tips, and don't miss our next video on advanced graph techniques.